Chapter 8. We've up to this point, we've looked at some of the more common elementary steps in the mechanism. Now what we're going to do is we get back to reality and put those steps together into a reasonable reaction mechanism, full total reaction mechanism. So in order to do that, there's a competition going on between the substitutions, eliminations, and whether they're bimolecular or unimolecular. Now, I'm not sure. I'm pretty sure that they're going to stick some protonations in here, proton transfers. I mean, that only makes sense because it's such a common step. So the title doesn't tell the whole story. This is just a review. When you have an SN2 reaction, remember, well, there's something to that. An SN2, this means bimolecular, this means nucleophilic, and this means substitution. Right, so when two molecules come together, while one bond is being formed, another was being broken. And we have we focus our attention very often on the leaving group because a good leaving group will promote this type of reaction. So for an SN1 reaction, we just substitute this one, and it's a unimolecular. Nucleophilic substitution. In other words, it's strange the way a bimolecular only requires one step, but a unimolecular requires two steps, because in a unimolecular, the leaving group leaves first and creates a carbocation, and then the nucleophile can attack. So it looks like, generically speaking, we had the same outcome. It is a substitution. So remember, back in general chemistry, when we were trying to put mechanisms together, if we had, say, A plus B equals C plus, I'll make that one up so it's clear. But the overall reaction is, say, 2A plus B equals 2C, something like that. So we're using one of these A's and one of these B's to make a C and an intermediate. That's an intermediate. Then the intermediate is consumed in the reaction with, let's see, I guess it would have react with another A and produce another C. So the intermediate gets used up. We don't actually see it. And in this particular, in this unimolecular nucleophilic substitution, the carbocation is an intermediate. Now, sometimes if you've got the technology, you can identify these, but it has to be very fast and very sensitive to see them. Most often, this is a construction so that we can rationalize what's happening. Okay. So from our perspective, that's what it is. We're just trying to make sense of it by introducing a carbocation intermediate. And we can be pretty confident that that's happening because of the outcome. So the overall reaction doesn't show you the intermediate. Excuse me. In this overall reaction, it looks like a bimolecular, right? But if we propose a unimolecular mechanism, then we have to go to leaving group goes first, then the nucleophile attacks. All right. From an energy standpoint, the intermediate is kind of a dip in the energy trace for this reaction. The intermediate is definitely more stable than either of the transition states. Okay, so we're saying that it's stable enough to sit there and make itself available for attack. Otherwise, if it were at higher energy, it wouldn't be there long enough. It may be reactive, but it would be in such a metastable state that it would disappear almost instantly. And it wouldn't be available for the nucleophilic attack. So we have to get a dip in that energy. This type of diagram is one that, well, it's a different, we're going shopping in a different store when we're talking about making things like nitroglycerin. The nitroglycerin, we pack a lot of energy into that molecule, but the nitroglycerin molecule is kind of in one of those dips. And then if you look at it cross-eyed, it'll go to the next transition state and decompose. It's very unstable. So even though it looks like it's more stable than the transition states, but it's not very stable overall. It's very reactive. Okay, so we take another look at the elimination types of reactions. We can also have a unimolecular or a bimolecular here as well. And this bimolecular elimination, requires that two species interact, they collide, and very often the attack is from a base. So it's looking for a hydrogen. So that's the distinction between a nucleophile and a base. They both have, the Lewis bases have electrons available. Nucleophiles have electrons available. But we distinguish the two based upon what they're attacking. The nucleophile tends to attack carbons, and the bases tend to attack hydrogens. So if we look at the stability of the conjugate acid of that base, then that acid is very, very, very weak. Okay, so if we have this base, and it has negative charge, but if we look at the reaction where we actually strip a hydrogen off of water, then we have this HB, it's neutral, and then the OH minus. Let's see. So what we're saying is, for this to be a very, very good base, that has to be an extremely weak acid. Okay. Okay, so the base attacks a hydrogen, and it breaks a bond. This heterolytic reaction breaks that hydrogen-carbon bond, and then those electrons have to go someplace. So they usually go to make a pi bond with the neighboring carbon. And then, because now we've got 5 bonds to the carbon, the secondary carbon, actually the beta carbon, something has to give. So if you've got a good leaving group attached to it, then it will go and take the electrons with it, so that carbon won't exceed its octet. That's the basic concept behind elimination reactions, and in particular the E2 type. So we need a very strong base, usually, and a good leaving group to be an elimination type reaction. If we go to E1, similarly, the leaving group leaves. It leaves behind a carbocation. And this is an intermediate that we really can't see. And as a consequence, that carbocation wants to be stabilized with 4 bonds, with an octet. So we break the carbon-hydrogen bond, and we can't let that hydrogen float free, right? At this point, that's when the base attacks. After the leaving group leaves, then the base attacks that hydrogen so that we can break the bond, satisfy the carbocation, and not leave a free hydrogen floating around, because they don't do that. And we end up with the same products. All right. So this is an overall E1. Okay. And all we're saying here is, in this scenario, is if we look at it this way, we can't tell whether it's an E1 or an E2, the overall reaction. We have to have some indicator as to what the mechanism is. And that's what we're trying to deal with in subsequent slides. Okay, so here we have just like the SN1, we have the E1, which has an intermediate carbocation, and it's slightly more stable than either of the transition groups. That's about all you can get from this one. Okay. So there are actually 2 ways to look at preferences in reactions. So I have to go back and dig deep into your mind. The difference between kinetics and thermodynamics. Thermodynamics doesn't care about the intermediates, right? So we're basically looking at kinetics, right? Which one happens faster? And that means we have to look at rate laws corresponding to the differences in their free energy diagrams. So generically, and these are the places you will find this information in Chapter 8, Section 6, 7, 8, and 9. And if we look at each of the rate laws, then we see that the SN2 rate depends upon 2 reactants, right? And the E2 depends on 2 reactants. The SN1 and the E1 depend only on 1 reactant. And and we're saying that this rate, even though it has 2 steps in it, the SN1 and the E1 rates are dependent upon the leaving group leaving, right? That's the RL, the concentration there, the leaving group leaving, because that is the slower step, right? That's the bottleneck. That's what we're trying to decide. Which one is the slow step? Come on, there we go. I think I just said that. The difference between SN1 and SN2 is in the way that they depend on their reactant concentrations. Right, the SN2 is going to depend on concentrations of 2 different reactants. Now those, of course, you remember the decoloration of food dyes with bleach that we did in the lab. In order to actually evaluate the contribution of the nucleophile and the leaving group substrate, is we have to take one to such a high concentration it doesn't change. Then we can investigate one, and we do at least 2 experiments at different concentrations for the high concentration component. and then we work out what its power is. Okay. All right, that's enough for that one. We can look at this one the same way, right? We see the dependence in E2 depends on the concentrations of two components, whereas E1 only depends on one. And the reason for that, I think, is that, if we go back, let's go back to the energy diagram, like here. Okay, which one of these steps is going to be the limiting step? Which one's going to happen faster? The one that has the lowest activation energy is the one that goes faster, right? So the one that slows things down is the one that has the highest activation energy, and that's the first step, right? To go from overall reactance to that first transition step is a much greater jump than to go from an intermediate to the next transition step, okay? I had to do that for myself as well as for you guys. Okay. All right, what are we trying to show here? Rate determining step. Okay, we already talked about that. We know that the rate determining step is the slowest step in a sequence of mechanism steps. So for SN2, because the mechanism of SN2 reaction consists of just a single step, that has to be our rate determining step, right? And we know that generally speaking, unimolecular steps are faster than bimoleculars because of the probability of two reactants meeting each other with sufficient energy and orientation to precipitate a reaction. Whereas with a single step, it depends on itself. All it has to do is crash into something, even the walls of the container, to transform some of that energy into a broken bond. And then tertiaries are almost impossible. Right? We don't even look at tertiaries. Oh, and notice back here, notice that the orders for each one of these, they're one, because there's only one each. So for mechanism steps, we can take the mechanism stoichiometry and infer orders for that elementary step. Whereas in the overall, remember the overall reaction, you can't do that. You can do it for elementary steps, but the stoichiometry doesn't tell you anything in an overall reaction as far as kinetics goes. Okay. So this is the rate determining step in an SN2 reaction. The only step, actually. The only step is the rate determining step. That's why we set it up the way we do for the rate law. Okay. SN1, we're looking at the first step is the slow step because of its increased activation energy. Okay. All right. I didn't realize I had a slide on that. But that's what they're saying in this slide. It's the energy barrier that slows down that first step. Okay, if we actually compare the rate laws, for the E2, both reactants concentrations are in the rate determining step. Whereas if we treat it as an E1 reaction, then we can only include the concentration of the substrate. So I'm thinking we could have the Lewis base and the substrate in the reaction mixture at the same time, and one or the other, the E1 or the E2, is going to dominate as the mechanism. So the key is, how do we tell the difference? That's what I'm thinking. All right, this is a reminder of molecularity. Every time I hear that word, I think of that episode of MASH where Father Mulcahy was his name, and he was, I don't know what the storyline was, but he used this word jocularity, and it just, I don't know, that comes flooding back. Those memories come flooding back whenever I see this discussion. Bimolecular, we know what that is. Unimolecular, we know what that is. All right, I'm not sure. This is a version of the Arrhenius kinetics equation. So the K for an elementary step happens to be some constant. That's what C is. I mean, just it's constant that is particular for this rate step, this step. And then the temperature in Kelvin, and then the E, which is 2.31 something, to the power of negative delta G, the free energy, over RT. So we've got temperature in two places here, and we've got the rate constant, which is the one with the energy, right? 8.3145 joules per mole K. And the free energy determines the K of the elementary step. All right. What does that mean? Maybe they're going to tell us. This is the transition state theory using the Arrhenius equation. We're trying to relate the reaction rate to the free energies of activation. So if we look at the rate constant, we see that it decreases as the free energy increases, right? They're inversely proportional. So as we increase the amount of free energy, the rate constant goes down, which is logical, right? It should slow the reaction. The rate constant should get smaller and smaller as we increase the delta G for any series of reactions. How about as we increase the temperature, the reaction rate increases for two reasons. One is the T is a multiplier in the expression, and it's in the denominator of the power. And if it's in the denominator, that means as it gets bigger, then the power gets smaller, and the influence of delta G becomes less. So for that reason, the rate constant is proportional to the temperature. As we increase the temperature, we get a greater rate constant. And that makes sense based upon the collision theory, because if you increase the temperature, you're increasing the energies of collision, and more and more of your molecules, remember that diagram where we have numbers of collisions. And this is energy. We usually have a spread of molecules, and only these have sufficient energy to precipitate a reaction. But if we increase the temperature, then we move that over here, and we got a whole lot more of them with sufficient energy. Okay. All right, so this is kind of a review. We can look at the rate laws in terms of elementary steps. And this just emphasizes the point I've already made, that when you have a balanced equation for an elementary step, you can infer the order of each of the reactants in your rate law from the coefficients. And then you can take all your elementary steps. If you've proposed a mechanism and you have several elementary steps and you have rate laws for each one, then you can combine those individual rate laws into a final rate law and compare it to the experimentally determined rate law. And that's one way to confirm or deny the proposed mechanism. If the mechanism doesn't fit the experimental rate law, then you throw it out. You have to go to a different one. So let me get this out of my way. There we go. So for that reason, our SN2 and SN1 reactions, the order is for each of the steps is always one. Each one of the nucleophiles or the substrates, they're always one. How about the stereochemistry of a nucleophilic substitution or an elimination reaction? Okay, here's where we get when we separate the sheep from the goats. It looks like the overall reaction is the same, right? We've come that far. By writing the overall reaction, we can't tell what the mechanism is unless we specify the mechanism. But if we do know the mechanism, then we can make some predictions about stereochemistry if there are chiral centers in the molecules or the potential for making chiral centers. That also is an approach. So what we're saying is that the SN1 and SN2 reactions may look alike, but they may produce different stereochemical outcomes, and usually do. What we have to do is try to get a handle on what influences those outcomes, right? And I've mentioned one of them before. When we have trigonal planar geometry and the attack can come from the front or the back, then that gives us roughly equal stereochemistries for that reaction. If we're restricted to only approach from one side, that usually, if the center of attack is a stereocenter and it's an S before the reaction, it'll be an R after the reaction. Let's see. Okay, stereochemistry of the reactions differ, whether that's a unimolecular or a bimolecular. So we're trying to describe what stereoisomers are produced, and this has very practical consideration for manufacturers. If the active molecule is a given stereochemistry, you want to control your reactions so that you come out with mostly the product you want, because that's where your money is. That's one reason. The other reason is safety, right? One stereoisomer might be clinically active and beneficial, and the other one might be non-beneficial or even deadly, like the thalidomide problem, right? They should have been more careful with that. Fortunately for the United States, most of the problems occurred in Europe, because at that time they didn't have the type of controls that they do now. And they were giving out poison. And an understanding of stereochemistry of reaction leads us to relative proportions of the stereoisomers. But if we know what to expect in the proportions of the outcomes, are we going to get R here and S here? How much of each one? Then we can either decide to use that reaction mechanism or to find a different one. Or if that's the only one, right, we know what has to be separated in the purification steps. All right. So if we treat this reaction, S1 chloro 1 phenylethanine, as an SN2 reaction, right? We have bimolecular, right? Where is that nucleophile going to attack? It's probably going to attack the carbon that's attached to the chlorine. right? So if it's set up like, let's just draw this part of the molecule. Let's see, it's sticking out. Like this, like this. This is your chlorine. So back here is going to be a hydrogen. All right. If this is sticking out to the front, then what's the most likely attack? Where is it going to occur? Well, the one that has the least interference, right? Chloride is a pretty big ion, and iodine is a huge ion. So it's going to attack most often where there's less steric hindrance, right? If this is sticking out this way, hydrogen in the back, it's going to attack. It's going to attack from the back. So when the chloride leaves, as a good leaving group, chloride leaves, now the iodine's on the back and the hydrogen's in the front. So we've flipped the stereochemistry from S to R. And the only reason, well, I said earlier that it always flips. It doesn't always flip the stereochemistry because it depends on the nucleophile of the leaving group, right? Because we have to take into account the priorities. Right. So in this case, iodine is a higher priority than chloride anyway, because of the atomic number. So it does. It flips the stereochemistry. I is in the back. It's the highest priority, just like chloride's the highest priority here. And this is okay. This doesn't work as stereochemistry unless I include this group. Right. Without that group, we don't have a stereocenter, right? We have two methyls on either side, so that was kind of misleading. So this inversion of the configuration is a stereospecific reaction to SN2s. Let's see, is it going to show us? Okay, yeah, here's the backside attack. It attacks from the, that's the same. That's the same molecule. They're putting the phenyl group down here as C6H5. And we're looking at an intermediate stage where we have 10 electrons on that carbon, which that cannot stand. So the chloride, that's an intermediate. And now we have the iodine is inverting the stereochemistry. This is known as a Walden inversion. Okay. If you dip your toes in the organic waters again, you're likely to be required to memorize the names for these different reactions. Right? If you don't go that way, then don't worry about it. Walden is probably the name of the researcher who first identified this and described it. A Walden inversion. Okay. By backside attack. Okay. Is a front side attack even possible? Well, there are two reasons. I mentioned one, the steric hindrance. All right, that the chloride is too big. It's not going to attack from the front side because that's where the chloride stands. But there's also charge repulsion. Right? It's not going to attack from the front side because this has a slightly negative charge and this is a full negative charge. They're going to repel each other. So that iodine is going to come in from the back side. It's going to sneak in the back door, in other words. Right. That's a forbidden reaction. And this is the idea of charge repulsion. Right? I explained it to you, and it's fairly self-explanatory, actually. Okay. You're going to solve the problem, I hope. All right, so we have this, the stereo center is where the bromine is attached. I'm pretty sure. Actually, we've got two stereo centers, don't we? Yep. We got two stereo centers. If we, 1, 2, 3, 4, 5, 6, this is a hexane. And 1, 2, 3, 4. So which one do we go from first? Is it 3 bromo or 3 methyl? Maybe we go. Maybe we have to go alphabetical. 3 bromo would give us a smaller number for that one. 3 bromo, 4 methyl. 2, 3, 4, 5, 6. Hexane. Okay, so we've got this strong nucleophile, this hydrogen sulfide ion, and we want the mechanism. We're going to draw the mechanism. All right. 1, 2, 3, 4, 5, 6. And then we have this methyl group, and we have this bromine sticking out, and this hydrogen sticking back. Okay, then we're going to attack with this nucleophile. All right. If we're told that this is an SN2 reaction, where's the best leaving group? Right there. Right. That means that the most likely attack is going to come on that carbon. Okay. So we're going to get this transfer here, and then that one's going to break. Right? Is this a front side or a backside attack? Has to be a backside, because this is negative and it's big. This is big, and they're both negative charge. Right? Slight negative, full negative. So a backside attack would give us what as a product? Let's see. Still got the methyl group sticking out.
Hydrogen in the front.
And now we have hydrogen in the front. Yep.
Back a little bit of fire on the back.
And then SH in the back. Mercaptan. I think that's called a mercaptan. Okay. Let's see. Oh, okay. And then we have the put all my products out here. There we go. And let's see. Yep. We got that attack. We got this one. And here. Oops, I left off my electron pair. Okay. That was fairly simple. We were, and it's simple because they told us the direction to go. The problem is if they don't tell you what direction to go, then you got to decide for yourself. That becomes an issue. In that case, maybe what we should do is, if we were going to treat this as an SN1, then the bromide would have to leave first. And then the sulfhydryl will attack. Okay, let's see. Oh, that's what we're doing right here. Sorry. We're using our former chlorophenylbutane as our example. All right, so if we treat it as an SN1 rather than an SN2, then the intermediate we get an intermediate like this, like that. This is chlorine. Okay, they're putting a methyl group out there. Right, that's not a hydrogen anymore. That's a methyl group. Because they didn't write a hydrogen, that's a methyl. Okay. All right, so if this is if we're treating it as an SN1, then the first thing that happens is the leading group leaves. Right? And we get, what do we get as a product? Well, this yields, let's see, keep my double bonds where they're, this yields a, like that, right? We've destroyed the stereochemistry, and now we've created a trigonal planar, 1, 2, 3, tertiary carbocation, which is reasonably stable, more stable than a secondary, obviously. So in that case, now we can get a front or a backside attack, both of them. So that gives us the ability to produce this product. Or this product. We could either have the iodine here, or we could have the iodine here. And that would leave us with the methyl group in front. You'd have essentially an equal share of either one because of the formation of this carbocation. And if I'm not mistaken, this would be called a racemic mixture. A racemic mixture is one that's 50-50, both isomers. Which means that if you put it in your, back myself into a corner, your polarizer, your, that's not the right term. You're detecting optical rotation. Then
Spectrometer?
you what?
Spectrometer?
Yeah, I don't think that's the right term for it.
No.
You put it in your polarizer, and you look for movement. Right? You get none. You don't get any optical rotation because you've got equal amounts of both. Okay, what this slide simply says is we can attack from the front or the back because the carbon now is sp2 hybridized. It's trigonal planar. And that's what we're trying to show here. Oh, I did get it right. Equal amounts, racemic mixture. Now that's if the environment is achiral. What we mean by that is we're not introducing another factor in there that would preclude the attack from one side or the other. If the environment is chiral, then you can do that. You can influence the attack. And that usually means when you form the carbocation, it's fixed to a stationary phase so that only one side is available. Okay. And that's one of the ways that we separate chiral compounds is on chiral chromatography. In other words, if your stationary phase has chiral extensions from it, then that will influence the partition. Excuse me. That will influence the partition between these two. One will lag behind because the chirality is more attracted to one or the other. So that's one way to separate chiral mixtures, is with chiral chromatography. Okay. Then if we have okay, another possibility, I see, that's why I put it in yellow. Another possibility is if we have another chiral center somewhere in the molecule and it's not involved in the reaction, then we produce diastereomers. And those can easily be separated. Okay. An ion pair is formed when the bond to the leaving group breaks, but the electrostatic attraction keeps the leaving group associated with the carbocation. All right. So what happens if we do form these ion pairs? Where else did we see ion pairs in general chemistry? In mine's working slow today. Can't remember the term. When we were doing, I almost had it. Boiling point elevation, freezing point depression, osmotic pressure. Those come under what class? Can't remember the term now. But if you introduce your say we're looking at delta T equals I K and molality. This Van Hoff factor, say if you have sodium chloride as your solute, then you would expect this to be 2 because it breaks up into 2 ions. But at high concentrations, you get ion pairing. And that decreases this to say 1.85 or something like that. So this ion pairing is not a new concept. We're just applying it differently. And stop trying to think about it, and then I'll get it. Okay. Now, my question is, under what conditions can you expect this ion pairing to occur? That's my question. Because a nucleophile could be paired from either side of the carbocation plane. But I suspect that if it's leaving from one side, it's going to stay close to that side. And that again would favor a backside attack. Okay. So here's the idea. If you have more than one stereocenter, then what you can produce from one of these reactions, this SN1 reaction, is a set of diastereomers. In other words, they're not mirror images of each other. Because we didn't touch the stereocenter with the hydroxyl on it. We only reacted with the one that had the chlorine on it. Okay? And that produced an equal mixture of front side and backside attacks for the iodide, but we still have that other stereocenter, and that means that we only changed one of the stereocenters, and that gives us diastereomers, which is not a bad situation, especially if you want to separate them easily. Okay, let's see. That's enough said about that one. We're going to form these diastereomers in unequal amounts. Okay. what we're saying here is, depending on which one is the more stable conformer, then we can limit with the other group, if it's close enough to the reaction center, we can limit the backside or front side attack. Right. Remember our was it Newman projections, right? Where one conformer is favored over the other, then we can have that. In this case, the hydroxyl should electrostatically impede the attack from one side or the other, and we tend to form unequal amounts of the diastereomers. All right. Let's make problems more difficult, why don't we? See if we can stump the band. So we've got this molecule. Let's see. And we have a methoxy group here. So that's a chiral center. We have a hydrogen over here, of course. And this one is bromide this way and methyl group this way. I'm going to draw that in there. Okay. So, what's the question? Assuming it takes place by the SN1 mechanism, will the reaction produce a single stereoisomer or will it produce a mixture of stereoisomers? It'll produce a mixture, right? If it's an SN1, then this one's going to leave and produce. We still got this stereochemistry down here. And now we have a carbocation in here with, well, I drew that in this is a methyl group and put the carbocation there. So that's the first step that's going to happen. This is going to, let's see, this is going to leave. Right, that's going to leave and give us this carbocation. Then what does the iodide do? Well, the iodine can theoretically attack from either side. Right? It can attack from this side or it could attack from this side. The problem is, do we have any type of interference here? Well, this is kind of far away. I mean, it'd be worse. It'd be easier to predict if it were on this carbon. But on this carbon, we could potentially introduce. This would not want to be on the same plane as that methyl group, right? So maybe it's over on this side, and then okay. Here we go. Okay, did I get this part right so far? Yeah, that's good. Then we could produce, if we get front side and back side attack, then we could produce these stereoisomers. All right, and then our hydrogen over here. And we could produce either let's see, iodine, right? With the methyl in the back, or we could produce this one. With the iodine in the back. Oops, negative. And the methyl group would be sticking out here. So those are the possibilities, those two diastereomers. Now, Okay. I think what the author is saying here is that you're going to produce equal amounts of each one because this group is too far away to influence the backside and front side attack. If it was on this carbon, we'd have a different story. Yep. Okay, we'll go to E2s, elimination reactions. Let's see, how are we doing on time? A little after 10. All we have to do in the lab is just go in and weigh our product. I looked in on it this morning, it looks pretty dry. Okay, for E2 reactions, the base, and for convenience, we're using hydroxyl here because that's an extremely strong base. Either a Bronsted-Lowry or a Lewis base, it's extremely strong. So, which hydrogen is it going after? Well, it's going to go after the one that's on the adjacent carbon to the leaving group. So we have to identify what's the leaving group. The best leaving group in this case is the bromine. So it's going to attack that hydrogen that's prominently shown there. And when it does, it produces a double bond between the alpha and the beta carbon. Right, that's E2. That all happens at once. So in this particular reaction, we do have stereocenters, right, at two locations. And they're identified as S and R. And the bromine is attached to the one. So that the S is where the bromine is located, the R is where the methyl group is located. And in this case, the way it's written, the hydrogen is anti to the bromine. And that stereochemistry should be preserved in the E or Z version. Right? We should get no Z isomer in this situation. Now, here's the other reason that they're anti is because of steric hindrance, right? Those phenyl groups need to be anti to each other because they're so huge, right? That is the most stable. If you rotate them around to this gauche position, then they start to interfere with each other. And there are two different gauche positions, and those are not acceptable for this reaction. So the conformation in which the hydrogen and the leaving group are anti to each other, referred to as anti-coplanar or anti-periplanar. I like coplanar better. Peri is just hard to say. It doesn't mean much. If they were coplanar, they'd be in the same plane. Well, actually, they are in the same plane. That's how they're drawn, with just lines. So the hydrogen and the bromine are in the same plane, but they're anti to each other, and they're coplanar. Okay, so for this reason, the hydrogen and the bromine are anti to each other because the phenyl groups are anti to each other. And we show that with this I just used the term earlier.
Lewis structure.
No, it's not Lewis. You know which one I'm talking about? No. No, the way that we draw the circle and the crosses. Almost had it. I'm gonna have to write these things on the board when I think of them. Newman. The Newman projection. Newman projection is very useful in these cases where you are trying to determine particularly steric hindrance, but even electrostatic repulsion too. Okay. So an E2 reaction as opposed to an E1 reaction is favored when the substrate is in the anticoplanar conformation. And we're trying to show here electrostatic as well as steric hindrance. All right. What if we have this one, two, three, four, two bromobutane. We have this 2-bromobutane. And we're attacking it with, since this is an elimination reaction, that CH3O, where did it come from? Came from methanol, right? Came from methanol. So somehow we caused it to do this number. Caused it to do this number. And the hydrogen went someplace else. So this is a very, 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 very weak acid, which makes this an extremely strong Lewis base. Okay, so it has the possibility, since the leaving group is on that number 2 carbon, and we have 2 hydrogens on the neighboring carbon that are available, which one does it go for? Right? If it goes for the top hydrogen, then we leave the bottom hydrogen alone and we form a double bond. If it goes from the bottom hydrogen, then we form another, well, actually, you know what? It would probably work better if we do this. Right? We know it's going to be like that because we want to minimize interference. Right? If we look down that bond, then we've got, say, in the front, we have a methyl group. And then we have a hydrogen here and a hydrogen here, right? And on the other one, we have a bromine and a methyl. So the methyl is going to be over here, right? Less steric hindrance. The bromine could either be here or here. Yeah, actually, it could be on either one. And this is going to be, let's see. That's a hydrogen. Okay. So if it's in this position, then this hydrogen is going to be attacked by this group. Right? Break that bond. Is this is an E2? Okay, so these electrons are going to go. Actually, we can't show them because that bond is in and out of the board. But if it's in this conformation, when the attack occurs, what are we going to get as a consequence? Well, the double bond is going to stop the rotation. So whatever this happens to be, when that occurs and the double bond is formed, then that's going to stop the rotation for the bromine to leave. And we get two possibilities. You either get the methyl groups, let's see, the highest priority would be methyl, right? You get the methyl groups on the same side, or you get the methyl groups on the opposite side. Right. This would be on the opposite side. The methyl group could also, once we form the double bond, it could have occurred in another conformation in which the methyl groups are ghost to each other, right? So I would say that the Z conformation is the minor product, right? Because of that steric interference, and the E is the major product. There we go. They're trying to show us with the dash wedge and a plane of symmetry in the middle. All right, so in the top one, what do we have? Looking down. All right, they drew it a little different than I did. But the hydrogen, the attacked hydrogen and the bromine leaving group are anti to each other. And in the bottom one, they're coplanar. I mean, they're not anti, they are coplanar. Let's see. All right, we're putting methyl groups on the same side. Yeah, that's in a ghost persistent. I didn't draw that one. The bottom one is the one I didn't draw. The top one is the one I did draw. And the top one tends to be the preferred. Right. Okay, how about an E1? What would happen if this were an E1 reaction? If we have the same setup, right? No, we have a different setup because we got phenyl groups. Yeah. Okay. We're putting phenyl groups in there because of the steric hindrance, right? That makes the E1 more likely. Okay. So what would that do? That would pretty much guarantee that the hydrogen and the bromine were anti to each other. And the major product then would keep the phenyl groups anti to each other, which would give us the E conformation rather than the Z. The Z would then be the minor product. So with the E2 tends to be a minor product of Z. Well, and the E1 also. Okay. So we can't really use that to determine which one's which. It has more to do with the size of the attached groups. Okay, this is what I was trying to show with the Newman projection. If we try to form a double bond, look at it this way. What's the outcome, right? We can't blame the outcome on the leaving group because it's the same group and it leaves as easily from one as from the other. So the outcome then is that we focus on how stable, is there any strain in the product, right? And in the Z conformation, you have serious steric strain with those phenyl groups on the same side. Yeah. So the major product is definitely going to be the E conformation. Okay. All right, proton transfers, here we go. And carbocation rearrangements. I knew they couldn't leave these out. Is it called polarimeter? I think that's what it's called. Polarimeter. These are the simplest examples, the substitutions and the eliminations. They have, the ones have two steps, the twos have one step, and in many instances, we will have to incorporate other types of steps, Right? The proton transfers or the rearrangements, depending on which ones give us a more stable intermediate. These are the most common additional steps. The proton transfers are very common. The rearrangements, carbocation rearrangement in particular, is very common. These rules apply to all reaction mechanisms. Okay, so we got some rules that help us try to decide, since, like I said before, if you're not given the mechanism that's being proposed, then you got to decide which one is the most likely. And that's what these rules are supposed to do. So, rule number one, avoid the appearance of incompatible acids and bases. Strong acids generally should not appear in the mechanism under basic conditions. That's pretty self-explanatory. Strong bases shouldn't appear in mechanisms under acidic conditions. Because proton transfer steps are fast. If you try to include bases and acids in the same mechanism, that's all you're going to get. Proton transfer. You won't get the reaction you're shooting for. Okay. So how do we identify strong acids and strong and weak acids and bases? Okay. Strong acids are either as strong or stronger than the hydronium ion, whereas weak acids are significantly weaker than the hydronium ion. How do we know the strength of the hydronium? Well, we look at the water. Right. If we look at water and its reaction, right, this is what you would expect for pure water to react. And what's the K here? The Kw equals 10 to the minus 14. All right, so this is the Kw. Or we could say in terms of acid reactions, this is the Ka. Right, this would be an acid and this would be a base. So this would be the conjugate acid of the base. And this would be the conjugate base. All right, we can say from either side, if we say this acid and this base, this is a very weak acid, this is a very strong base. This is a very weak base, this is a very strong acid. So these are both relatively strong. Because this is a weak term. Strong bases are usually as strong or stronger than the hydroxide ion. Any acids whose pKa is less than 0 will be a strong acid. That goes without saying. Any base whose conjugate acid has a pKa that is greater than 14 will be a strong base. Okay, that's self-explanatory. So we're given examples. Strong acids. That's a strong acid. The protonated methanol. He's trying to call me. Oh, Dr. Thomas. I missed it. I'll have to call him back. And then a protonated methanol is a very strong acid. And what is H3CCH2 plus? That's a deprotonated ethane molecule. That's a very strong acid also. Let's see, weak acids. Well, definitely water. Water is a weak acid, right? Because of that K. Ammonia
is actually not much of an acid. It's better base. Ammonium is also a weak acid, and the methylammonium are weak acids. Strong bases. Anytime you see a hydroxyl, you know you got a strong base. If you have an amine ion, that's very strong. If you have a methyl ion, carboanion or carbanion, then you've got a strong base. Or if you have H minuses. Now this is for convenience. That does not occur independently in a solution. But remember, we propose this as a simplification. So that would have to be some hydride, like a metal hydride would produce this anion. Examples of weak bases. Well, water's a weak base. Ammonia is a weak base. Chloride, bromide, iodide, those are weak bases. And hydrogen sulfate and the carbonate anions, those are weak bases. Okay, so when we write a reaction, typically we put the most often we're going to put the substrate as a reactant. Right? In this case, the phenylmethanol or benzyl alcohol is a substrate. And then sometimes the nucleophile or the base, depending on the reaction, is placed as a reactant, but sometimes also it's placed as a on the arrow. Right. In this case, KOH, that's the base. OH is the base. Well, actually, these are basic conditions, right? This is overall. This is an overall reaction. So you're going to have lots of stuff on that arrow that could be separated into individual elementary steps, right? We have that OH minus as a base, and we have the one bromo nitrile, one bromo ethane nitrile as a you know what? Which one's the nucleophile? Bromine's the leaving group, so that should be the substrate, right? Bromine's on the substrate. So the substrate, they're putting the substrate on the arrow. And the phenylmethanol is the nucleophile. Okay. I'm not a synthetic organic chemist, so don't ask me why they do it that way. Okay, this explains what they're trying to do. This is an unreasonable SN2 mechanism involving an alcohol under basic conditions, right? We would not expect this to happen. The reason being, when this hydroxyl attacks the carbon closest to the bromine, and we expect the bromine to leave, then what would that give us? Well, we'd have a positively charged oxygen attached to that nitrile. And that's a strong acid. But these are basic conditions. That's what we're trying to demonstrate here. We're producing a strong acid under basic conditions, and that won't happen. Okay, I think that was the whole point of that slide. This is a reasonable mechanism where under basic conditions, first we get the proton transfer. And that leaves us with a negatively charged oxygen on our substrate and a very weak acid, water. Then the oxygen can attack the carbon and the bromine can leave. Then we can get that's a more reasonable approach rather than, they're both SN2 propositions, but the proton transfer has to occur first because we have such a strong base there. And we have the hydrogen attached to that oxygen on the benzyl alcohol is that the bond between the oxygen and the hydrogen are very weak because the oxygen is drawing electron density away from the hydrogen. So that makes it susceptible to the strong base. That's why we get the proton transfer first. Then we can go for an SN2 reaction. So the reaction conditions dictate what steps are going to occur first, and maybe you'll get the outcome you want and maybe you won't. Okay, let's change the conditions to acidic now. So we've got sulfuric acid in here. We're pumping the environment full of hydrogen ions, or hydroniums actually. And we're given under acidic conditions, this 2-methylpropane-2-ol is going to undergo, is it an maybe SN2? Yeah, it's probably an SN2 reaction. We're gonna substitute the bromine for the hydroxyl. Now, can we do that? If the hydroxyl comes off, right? Well, hydroxyl is not a good leaving group. So when the bromine attacks, the bromine would rather be by itself, right? It's already left, right? Under acidic conditions, you got the bromine ion. So what we're probably going to do is protonate that hydroxyl, and that will turn the hydroxyl into a good leaving group, right? The OH2 plus, right? Let's see, this one, got that, and this. Right. So under acidic conditions, we're going to have hydronium ions, right? And we're going to, one of these protons is going to be transferred to this one, and that would leave us with that. What does that look like? Looks like water, doesn't it? H2O. That's an excellent leaving group because water is very stable. Okay. So let's see, H2. These two electrons would break there. That would give us water. And we would end up with a tertiary carbocation. That's what I think first step's going to be. All right. Right. The first one is not going to happen because the hydroxyl is a base and these are acidic conditions. Right. That's definitely not going to happen. Plus, hydroxyl is not necessarily a good leaving group anyway. But if, on the other hand, we do a proton transfer, actually, that was the wrong direction, wasn't it? Movement of electrons. And that would leave this one as water. Okay. So that would be this one and this one. And that would give us this good leaving group. Then we could transfer these electrons. That would go here, and then we'd be left with a carbocation. And the carbocation then could be attacked by the nucleophile, which is bromine. So our bromine then could attack there, and this would be a coordination we form a coordinate covalent bond because there are no electrons being contributed from this carbocation. They're both coming from bromine. And that would leave us with bromine here and the methyl groups. Okay. All right. This is an SN1. SN1. Okay. Oh, yeah. Yeah, it has to be an SN1. Why? Because the water, that heterolysis step is the determining factor for the SN1, right? The leaving group leaves. Right? We get a proton transfer, but the SN1 part of the reaction is the water leaves. And then the bromine can attack. All right. So how are we coming on number of slides? I think there was like over 70 of them, weren't there?
We're 60.
Okay. Okay. All right. So mechanism for the elimination reaction shown here. Assume it takes place by an E1 mechanism. All right, let's see. We have methoxycyclohexane under acidic conditions, and we're adding heat. We haven't talked about the effect of heat yet. That may come in the second semester, but heat or cold, the temperature does have an impact on the outcome of reactions and which mechanism is preferred. But we're saying that we've got an elimination reaction that produces cyclohexene. All right, what is probably the leaving group? Well, it's going to start with this methoxy. But the methoxy itself is not necessarily very stable, especially since we're in acidic conditions. The methoxy wants to be methanol. So what we're probably going to do is, what are we going to do? Okay, I guess that's reasonable. Oh, what conditions were these? Acidic conditions. Okay. Under acidic conditions, an E1 reaction means the methoxy leaves, but that's a very strong base. That's not reasonable, right? Under acidic conditions, if we produce that methoxy anion, it's immediately going to be neutralized, right? That's not a good mechanism, right? So what first we're going to do is under acidic conditions, we're going to protonate that methoxy group. Right? That makes it an extremely good leaving group. Methanol is very stable. And that will leave behind, that proton transfer will leave behind a carbocation, a secondary carbocation, which is stable enough. Then the water can, under acidic conditions, then the water can acquire a hydrogen and can eliminate the hydrogen and leave us with a double bond. That's a more reasonable mechanism. So we got proton transfer, heterolysis for the leaving group, and then elimination of hydrogen to form the double bond. Okay. Intramolecular versus solvent-mediated proton transfers. Okay, we're still talking about proton transfers. Oxyrain used to be called ethylene oxide. It's very strained, three-membered ring. All right, so it's going to be easily, that one of those bonds is easily going to be broken. So if we treat it with ammonia, which is a base, right, and it's going to produce 2-amino-ethanol, right? So what we're doing is we're substituting the amine group for the oxygen. Actually, no, we're not. We're breaking the bond. Excuse me. We're not substituting. You know, this is not one of the reactions we studied, because there's no leaving group. Right? There is no leaving group. We're taking advantage of the strain of that bond. Okay. So the ammonia has a pair of electrons that are available. The bonds are weak due to strain between the carbon and the oxygen, but one side is usually more strained than the other. And we can't tell which it is because this is symmetrical. So it could attack the other carbon just as easily. But the ammonia is going to attach to the carbon, and then the heterolysis is going to occur between the carbon and the oxygen. And that leaves us with a negatively charged oxygen. So in order to get the hydrogen to that one, how are we going to get the hydrogen from the ammonia side to the oxygen side? Because they're not, well, they are adjacent. They're on adjacent carbons. So this is a rearrangement, I think. It should be a rearrangement. No, we're saying they're actually 3 nuclei apart, so that's not going to occur. An intramolecular proton transfer is not reasonable because they're too far away from each other. Okay, I was barking up the wrong tree. So what do? We do an intermolecular instead of an intramolecular. The proton from the ammonia is transferred probably to a water, and then it is deposited on the oxygen. Yeah, there it is. Well, actually, it goes the other direction, right? The oxyanion is going to pluck a hydrogen. We get a proton transfer off of water, and then the hydroxyl is going to pick up a hydrogen from the ammonia. So we get 2 proton transfers to reconcile that charge difference. The reason we want to do that is because separation of those charges makes a very unstable molecule. More stable is neutral. Oh, that was, okay, we're still rules. Avoid intramolecular proton transfer steps. That's rule number 2. What was rule number 1? Maybe I better write these up here. Oh, okay, rule number 1. Acid base incompatibilities. Okay, avoid those. 2, is the one we just talked about, wasn't it? Yeah, rule 2. Intramolecular proton transfers. This is avoid. Avoid that one. Avoid this one. Just in case we get one that are preferred. Okay. Avoid termolecular steps. Yeah. Avoid termolecular. We don't have to spend a lot of time on this one. Well, in the first place, term molecular steps are probably going to exceed the 3-arrow rule anyway. We know that is not kosher. How about carbocation rearrangements? These carbocations are very reactive, so we only rearrange when it stabilizes the intermediate. For SN1 reactions, we're going to get a substitution at the carbon next to the carbon leaving group. Okay. So for this SN1 reaction, the leaving group would leave first, right? We get the heterolysis. That would produce a secondary carbocation. If we do a proton rearrangement, then we can get our carbocation on a tertiary carbon, right? So the 1,2 hydride shift would give us a more stable tertiary carbocation. Then we could coordinate with the water molecule because the carbocation is very reactive and water is a reasonably good Lewis base in this case. And then we form this positively charged group that needs to get rid of a proton. So we proton transfer back to water. And this overall, it looks like what we're doing is we're creating an acid environment over time. Yep. Okay. 4. Favorable 1,2 hydride 1,2 methyl shifts will usually win. If an energetically favorable 1,2 hydride shift or 1,2 methyl shift competes with another possible elementary step, the carbocation rearrangement is usually faster. Okay. It really, really wants a stable carbocation. And in order to do that, we're going to get a shift before anything else happens. If you end up with a secondary carbocation and the possibility exists to form a tertiary carbocation, it's going to happen before anything else happens. Right? So 4 is 1,2 hydride or 1,2 methyl, right? Methyl shifts are kinetically favored. Okay. We're not going to go from a tertiary carbocation to a primary. That will not happen. If we're okay, so we're taking that tertiary carbocation in the first 1, 2, 3, 4. Yeah. That tertiary carbocation, we're saying the 1,2 hydride shift is not going to occur. But the 1,2 methyl shift might occur even though we've still got a tertiary carbocation. Which one is more stable? The one that's adjacent to the phenyl group, because it's resonance stabilized. And then that's the species that will continue with the SN1 reaction. We get a coordination and then a proton shift. Okay, so we're trying to explain why the alcohol attacks that carbon and not the previous carbon. My guess is that you will get minor components from the previous one, but it's not by any stretch of the imagination major product. Okay, resonance delocalized intermediates and mechanisms. Substitution did not take place on the carbon with the leaving group. Okay. This is acidic conditions. Okay. This is an SN1 mechanism, no carbocation rearrangement. Let's see how we explain that. Okay. It's acidic conditions, proton transfer is likely. Yeah, okay, that makes sense. So what would happen then? Well, we've got a good leaving group, right? So that's going to form, we're left with chloride, but we've got water as a good leaving group. So the leaving group leaves us with a 1, 2, 3 tertiary carbocation that can resonate with our double bond. Right. So that makes okay, we're resonating a tertiary carbocation with a primary carbocation. There's not going to be much in the way of primary carbocations available, even though it's resonating and it's stabilized that way. So what happens, I think the chloride could attack from the front or the back on that tertiary carbocation. Why doesn't it? Because the primary carbocation is more reactive. That's the only thing that makes sense. It wants to attack the more reactive species. We still have little steric hindrance. Okay, when a resonance structures are incorporated into a mechanism, keep in mind 2 important points. Conversion of one resonance structure to another is not an elementary step. An individual resonance structure is hypothetical, and one true species is most accurately represented by the resonance hybrid. Okay, well, that goes without saying. Resonance structures are just different depictions of the same species. This leads to the second point. When an intermediate has 2 or more resonance structures, any resonance structure can be shown to participate as a reactant in the next step of the mechanism. Okay, so they're saying you get what you get, right? They're not trying to explain why it attacks the primary carbocation and not the tertiary carbocation. Okay. Utilizing resonance structures in mechanisms. All right, that doesn't tell me anything. All right. Well, that's as far as it goes. I mean, it could go a lot deeper, and that's for next semester. And you're probably happy to let somebody else do that.